Hello, class. This is Trigonometry at College of the Cycloids. Right now it is spring 2020 in COVID-19 lockdown, and that's why I've started making these videos. Today I bring you the last section in this book, and it is on parametric equations, graphs, and applications. This is section 8.8, and as I was saying, parametric equations, graphs, and applications. A lot of applications are physics-based, but I'm sure there's others. So let's just start you off with some definitions. A plane curve is a set of points, x, y, such that x is a function of t and y is a function of t. Where f of t and g of t are defined on an interval, some interval I, on some region. The equations x equals f of t and y equals g of t are parametric equations with a parameter t. So that's the mathy definition. Let's put it another way. In normal English, let's picture t as time. We can plot the x and y position of an object over time. So we often start at t equals 0, like launch time, and follow the object's path as time increases. So what we're doing is we're treating this, this is very much a huge physics area. We do this a lot in physics. But let's just dive into an example, and maybe that might clear it up. I've got some good DESMOS. I set one up today. I think you're going to like it. I think it shows it well. So let's just look at it. The first thing we're going to do is we're going to graph a plane curve. Defined parametrically. We're going to do it by hand first, and then I'll show you in DESMOS. And what we have is x equals t squared minus 1, y equals t minus 2, and we're going to have t be in the interval -3 to 3. I actually take it a lot bigger on DESMOS, so because it's easier to see a bigger thing over time. But for now, let's take a look at it. Best approach, by hand. Make a table. In one column, we'll have t, and we'll range through all the values, the integer values. Then we'll do x equals t squared minus 1, y equals t minus 2, and maybe we'll make a column for the ordered pair. That way it's easier to plot. I'm going to put little lines in every 2 so it's easier to read. So let's just go through it. Let's plug in -3 to each of these. -3 squared minus 1 is 9 minus 1, which is 8. So my x component is going to be 8. -3 minus 2 is just -5. Then we'll plug in -2. This ends up being 4 minus 1, which is 3. And then we've got -2 minus 2, which is -4. Plug in -1. 1 squared is -1 squared is 1, minus 1 is 0. And -1 minus 2 is -3. We get 0, -3. If I plug in 0, I just have the constants, -1, -2. And let's see, we plug in 1. 1 squared minus 1 is 0. 1 minus 2 is -1, so we got 0, -1. This is 3, this is 8. And we've got 2 minus 2 and 3 minus 2 is 0 and 1. So let's take a look at, let's plot those. Let's see what it looks like. Looks like x goes really big, but y doesn't have a lot of range. It goes up to +1, down to -5, over to -1. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'll start plotting them. The first one I have is 8, -5. That's down here at t equals -3. Then we have 3, -4. That's at t equals -2. 0, -3 is at t equals -1. -1, -2 at t equals 0. And then it starts going back to the right. We got at t equals 1, we're right there. At t equals 2, we're right there. And at t equals 3, we're right there. It looks like this object, whatever particle it is coming in like that and turning and then going like that. And we can even put little arrows on it, illustrating what direction the particle or object's moving as time increases. So it's a good idea. Maybe include little arrows, little arrowheads. To show the direction of flow. That looks like a parabola, doesn't it? It looks a lot like a parabola. Is there another way to graph this? Let's take a look. We're going to use those same equations. So let me put them there real quick. And we'll keep our picture on the screen so we can see. It looks like a parabola where the y one is squared, the x isn't. Let's see, how can we make this look pretty? So how can we write this? As one equation without a parameter. Without a parameter means we're trying to get rid of t. Well, this is the best way of going on doing it. Find the one that's got the smallest power on t, or whatever your parameter is. T is often a parameter, theta is often a parameter. Those are the two most common parameters in all reality. Time and angle. One thing I can do is I could solve this for t. If I add 2 to both sides, I get y plus 2 equals t. T, not 2, t. And I could plug that in for t right there. And I get x equals y plus 2 squared minus 1. And now that does look like a parabola opening to the right. But I thought I'd do something nice for you. Check this out. Here's that equation I just had, x equals y plus 2 squared minus 1. And these were our two parametric equations. I'm going to enlarge it for a second. And watch what happens as I let time play. The cursor's right here. It's going along. The point's coming along, going to the left. Right as it gets around to 0, it hits here and it starts going the other direction. Kind of neat, right? So it's what we're doing is we're tracking the x position and y position as a function of time. Where is this object located as time increases? And increasing is the common way of doing it. We don't have a means of going backwards in time, so we tend to not look at that. Okay. Let's take a look at, okay, that had just a regular equation. Let's take a look at a parametric equation that's got trig functions in it. X equals 4 cosine t, y equals 2 sine t, and we'll go from t in 0 to 2 pi. So I'll make my table. I'm not going to go crazy with time. Maybe every quarter of a pi, at least for the first part. And for the last half, I'll jump to maybe increments of pi over 2. I'm just trying to get a feel for what's going on here. So when t equals 0, cosine of 0 is 1, x equals 4, and sine of 0 is 0, y equals 0. So we have the coordinate 4, 0. If I put in pi over 4, cosine of pi over 4 is root 2 over 2. And if I multiply this by 4, I get 2 root 2. And what is that in a calculator? 2 times root 2 equals, it's about 2.8. If I plug in, oh, and then I got to do it over here. 2 times pi over, or root 2 over 2 is just root 2. That's about 1.4. I don't know why I had to look at that since I knew it was half of that one. And we've got 2.8, 1.4. And we're going to go through the rest. Let's see. Pi over 2, cosine is 0. Sine is 1. 1 times 2 is 2. And we get 0, 2. Now we're in 3 pi over 4. This is quadrant 2. X is negative, y is positive. So I'm going to have the same thing as the pi over 4, but it's going to be negative. Negative 2.8 and 1.4. We're down at pi. Sine is 0. Cosine is negative 1. We get negative 4 comma 0. Three pi over 2, cosine is 0, and y is negative 1. And 2 pi should get us back around to 4, 0. So this doesn't look like a very complicated graph. So let's take a look at what we got. But they're right out my outside my window, mowing the lawn and stuff. Let's see, t equals 0. We're at 4, 0. At pi over 4, we're at 2.8, which is close to 3, up to 1.4. That's t equals pi over 4. Pi over 2, we're straight up. And now we're way back over here. Negative 4, 0. This is t equals pi. So it looks like it's going like this. And the direction of travel is that way, counterclockwise. And then we get 0, negative 2. and we're back around, it looks like it's doing this. There's no reason the shape changes on top. What does that look like? Looks like an ellipse, right? So how can we write that? How can we get rid of the parameter t here? So this one's got a little trick, and I hope you like it. Let's write our initial equations that we had. X equals 4 cosine t, y equals 2 sine t. What we're going to try to do, rather than try to solve for t, take advantage of cosine squared t plus sine squared t equals 1. So I'm going to rewrite these in terms of cosine t. I'll divide by 4. I've got x over 4 equals cosine t. Y over 2 equals sine t. And now I'll square both sides. And I get x squared over 16 equals cosine squared. Y squared over 4 equals sine squared. Now we'll add them. Add the left sides and the right sides. So putting them together, I get x squared over 16 plus y squared over 4 equals cosine squared t plus sine squared t. But that right one is 1. And that is the equation for an ellipse. Good stuff. And we can see it goes counterclockwise around the ellipse. Kind of neat, right? And since I have t going for so long, it just keeps going. It keeps making loops around the same ellipse. Okay. Another skill we can develop is how can I rewrite equations in parametric form? So here's my example. Y equals x minus 3 squared minus 1. So two common ways of doing it is just make x equal t. X equals t. And that makes y equal t minus 3 squared minus 1. Okay. Another common way of doing it is use the interior and set that to it. Let x equal t minus 3. And now y equals t squared minus 1. This one doesn't change much. In fact, it actually looks like more work to track, doesn't it? This looks identical to this other than X and T, but now I got to track T and then X and Y. Here, I just plugged in an X and I got a Y. Here, I can plug in T and X and Y are pretty easily, quickly solved. Okay, so that's a couple common approaches to giving two parametric representations for the same equation. They both result in the same graph. It's just different ways of parameterizing it. There are some neat shapes that fall out of this kind of stuff. So let's take a look at like a cycloid. And I think maybe the best picture to do is show a wheel. And the wheel's rolling down the road. So let's say we got a point here, and as the tire rolls, it's down here. And as the tire keeps rolling, that point, the point on top goes down, this point goes up, might come back up like this. And this thing, as the tire rolls, this point on the surface keeps doing something like this. So let me write this, the words for it. So we've got a point on a circle, on the edge of a circle. Has its path traced. As the circle rolls to the right, let's say. It doesn't have to be the right, but that's the way I did it. The trajectory mapped is called a troc. Is it OI or IO? Let me look. I wrote it down. OI. And its parametric equations are x equals AT minus A sine T, y equals A minus A cosine T for T in negative infinity to infinity. A trochoid is one of the cycloids. There's other ones. If you want to check them out, I recommend looking at the multimedia library section. It discusses them. You're not getting tested on any of that. But it is handy to see how it graphs out. So let's graph one. Let's graph the cycloid. X equals 2t minus 2 sine t. Y equals 2 minus 2 cosine t. And we'll just do it while t is between 0 and 2 pi. going to write it in degrees because it takes up less room than writing the pies. These are all the 45 degree marks. And then we'll have a spot for our X and Y, just coordinates. So when t equals 0, this is 0 minus 0 is 0. And 2 minus 2 cosine of 0, 2 minus 2 basically is 0. So we start off at the origin. Here is where you don't want to use degrees. I did it for the list, but remember this is pi over increments of pi over 4. That's what we want to use. So 2 times pi over 4 is pi over 2 minus 2 sine of pi over 4 is minus 2 times root 2 over 2. What is that on a calculator? The 2's cancel. I have pi divided by 2 minus the square root of 2. 0.16. And here we've got 2 minus 2 times root 2 over 2. .59-ish. 90 degrees is pi over 2. So the x value is 2 times that is pi minus the sine value at 90 is 1. Pi minus 2, this is about 1.14. We do the same thing here. 2 minus cosine, 2 times cosine of 90, 2 minus 0, that's just 2. And you can see this gets pretty tedious pretty quick because it sucks where we have to plug in radians and then we have crappy decimals. The x value for this is 2 times 3 pi over 4 minus, doing the sine version is still root 2. So I've got 3 times pi divided by 2 equals minus the square root of 2 equals 3.30. And we plug that in here. We've got 2 minus 2 times negative root 2 over 2. So it ends up being 2 plus the square root of 2. 3.41. And this list keeps going. 180, we're at pi. 2 times pi is 2 pi. Sine of pi is 0, though. So we've got 2 pi is about 6.28. And then we've got 2 minus 2 times negative 1 is 2 plus 2 is 4. Now we're in quadrant 3 where both of them are negative. This is 2 times 5 pi over 4 minus 2 times negative root 2 over 2. So I got 5 times pi divided by 2 plus the square root of 2. This is 9.27. And the x value is going to keep increasing because t keeps getting bigger, but sine t is capped. And here we've got 2 minus negative root 2 over 2, which is 2 plus that. We just had that here. That's 3.41. Looks like the y value is starting to go back down. 270 degrees. This is 3 pi over 2. Sine is negative 1. So I have 3 pi plus 2. This is about 11.42. Plug it in here. We've got 2 minus 0 is 2. It looks like this is starting to go back down. So the next one should be 0.59 and then 0. What are the x values? I've got 2 times 7 pi over 4 minus 2 times negative root 2 over 2 ends up being plus it. 7 times shift pi divided by 2 plus square root of 2. 12.4. 1. And 360 is the same as 0. The y value hasn't changed, but this now is 2 times 2 pi minus 2 times 0. This is 4 pi, which is 12.57. Mapping it, not all that fun. The y values never go negative, and they're always between 0 and 4. That can help. I can focus my graph like that. And we go up to 12.5. So let's just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We start plotting our trajectory. That's at t equals 0. .16, 0.59 is right about there. 1.14 and 2 is right about there. 3.3 is a little bit past this, and we're up to 3.41, which is right about there. At 6.28, we cap at 4. And then it starts to come back down, 9.27. 11.42 is at 2. So it's going like this. And you'll find if you keep going, it goes like that. Okay. Cycloids are hard to get rid of t. deparameterize, maybe let's say that. Because there's t's all over the place. We can take a look at this though. And we just got to track how the thing's moving. Look how it's going. Boom, 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 boom. And then it comes down and bounces. Then it goes back up, comes back down and bounces again. And that's how that wheel is moving. This is a point on the edge of the wheel. All right. So that's cycloid. Yeah, I'm not testing you on this, but you should have seen it. So it's good, worth having seen. Parameterizing, you're going to do a lot of. You're going to do an awful lot of it. And when you get to pre-calculus and calculus more. And it's a really useful skill. Where is something that works in physics, chemistry, nuclear physics? Where's an atom's position? Where's the electron's position in chemistry? But we got some more fun stuff right now. So let's say Professor Hefe is a human cannonball. So here's this block, there's the cannon, and out flies El Jefe. Maybe I want a cape. Let's put a cape on. I got a cape. That looks like a moo-moo. That's a bad cape. Okay, so this is an application where something like this, we can parameterize it. An object that is thrown or launched shot, whatever word you want to use, with the velocity of v, and this is in feet per second. If you're in the metric system, it's different, the equations. An object that's thrown, launched with a velocity of v at an angle theta with the ground. So like it's sitting on the grass, here's the grass, that's theta. The flight can be modeled parametrically with this. X equals v cosine theta times t. Y equals v sine theta times t minus 16t squared plus h. T is the time in seconds. H is the object's initial height above ground. So how big do you think a cannon is? A human cannon. A human cannon. You think maybe I would start at maybe 10 feet high? Let's say for Professor Hefe. Hefe's human cannon. Starts 10 feet off the ground. I'm in the cannon. I'm not like at ground level. The cannon isn't submerged. Let's look at 3 different angles. Okay, so that's my cannonball. So my H is 10 feet. Let's say my initial velocity. Ooh, I'm flying pretty quick. Let's say 120 feet per second. And let's look at angles. Theta equals 20. No, let's do, what did I do in DESMOS? Well, I had the option of putting whatever I want in DESMOS. Let's keep them at angles we know. Let's go to the 30, 45, 60. Okay. At which angle will I travel the furthest? And at which angle will I be the highest? So let's see what we got here. Let's look at our equations. We've got x equals 120 cosine theta times t. Y equals 120 sine theta times t minus 16t squared plus 10. So I've got this set up in DESMOS. Do I have them both set up? I need to add the 10 there. I did. This was initially a golf ball problem, but that's less fun. Okay. So pi over 12, let's see. Pi over 12 is 15 degrees. Let's do 1575 also. Let's do 15, 30, 45, 60, 75. 90 is straight up. I'm not going to go any distance to the right. I'm going to go straight up, and there's no way to put a safety net over the cannon when I come back down. I'm just dead. I don't want to go at 90 degrees. We're not going to do that. So I have the equation set up here. B equals, so here we got B equals, I used B because it was easier to set up a parameter that shifted. I've got B set in as 120, and I've got my initial equations. Let's just see what it looks like as T goes down the list. Let's bring T down so I can use it easier. Oh. Doesn't make sense to start at -9. That's a negative launch time. Okay. So look at how I'm flying. Let's try that over. Notice we're starting off 10 feet up. Let me see if I can slow it down a little bit. And as it launches, I'm not at a very good angle. I'm not going very far. I'm not going up very high. I actually have it parameterized. We'll show how to do that in a second. This is the trajectory I'm following. So this shows it's got the peak and it's got the ending destination. So let's write those down. So theta, we're not going to do the computations. We've already shown how to do them. We already showed how tedious it already is. We're just doing 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees. So furthest and highest. "15 degrees, it looks like it goes up to 257.6 feet. And the height, is the Y value, 25.1. And I'm coming in at a hard angle. I can't imagine hitting a pool very well like that and being happy. Let's take a look at 30 degrees. 30 degrees in this is what? Pi over 6. Apparently I need to mute something on my surface. There we go. Looks like the farthest I travel there is 406.3 feet. And we go up 66.3 feet. Change that to pi over 4. Now we go 459.8 feet. And what's our height here? 122.5. And this works on all of them. I mean, we can watch it go the whole way. That's how this parametric thing does. It, like, basically we do an X line and a Y line. Where they intersect is where that particle or Professor Hefe is as he's launching through the air. I think that's kind of neat. The next one is pi over 3. $395.4 feet. Height is 178.8. And 75 degrees is 5 pi over 12. So I don't go very far. But I go up really high. Okay, so I was making the table over here. and we could have gone through and calculated this by hand. And in fact, when you get to calculus, finding the max height is really easy with calculus. Then algebra, to be honest. How did I get this equation right here? Let's get rid of the parameter t. Okay. So let me put the equations back up. Those are the two I started with. What I did is I solved for t on the x equation. Here I've got b in there. I didn't change it because when I put it in DESMOS, I left the b in so I could change the initial velocity anytime I wanted. I can make it so I go further. You know, stuff like that. It's like pi over 4 got the farthest. And you'll notice as v goes up, I go further. Which makes sense. I'm traveling faster. So what I did is I solved for t, divide by 100, v cosine theta, and I plugged t in right here, and I plugged it in there. So squaring that just gives me x squared over v squared cosine squared theta. And then we have v sine theta times x over v cosine theta. The b's cancel. So I've got tangent theta, sine theta over cosine theta times x. And that's where I got that portion. Good stuff? Well, that wraps up trigonometry. You will see a lot of this stuff again when you get to calculus. If you take pre-calculus, the way we're setting up our schedule, the classes, and don't know where it's going to end up, there's a lot of good stuff coming up. See some of these cool physics ones though? How far can we launch the teacher? It works with, you know, aerial fireworks. At what angle can we shoot it that we get the highest? And how can we figure out how to set the time delay so it blows up at the peak? Because we don't want it blowing up right as soon as it launches. It'll blow up someone's house or the field. And we don't want it till it waits till it lands, because if you're at a fairgrounds and you launch it up, that wind's going to blow it into someone's yard, and then it blows up in someone's yard. Again, you want it to blow up or detonate at the peak. And we can use this math stuff to find out good stuff. That'll close up this semester. It's been an honor being your teacher. I will have a video in the next couple of days on how the final is going to go. I'm still wrapping up the final things. It might be in my math lab. And with some of the straighter forward problems, not like the physics problems. Peace.